The Euler method approximates how systems change over time. These systems are described by differential equations, showing how something changes rather than what it is. The Euler method helps predict the future state of a system step by step, even when exact calculations are impossible. Imagine hiking a foggy mountain trail. You can't see far, but you know the current direction. You take a careful step, reassess, and take another. This step-by-step progress, without seeing the whole path, is how the Euler method works. It uses current change rates to estimate future states. We need it because many systems are governed by rules of change, not direct formulas. For example, a falling object's speed changes due to gravity and air resistance. Species population grows based on food, predators, and climate. A cooling metal's temperature depends on the surrounding air. We're given change rates, not direct values. Exact solutions are often difficult or impossible. Euler's method simplifies these problems into small, manageable steps. Each step estimates the next state based on the current rate of change. Smaller steps mean more accuracy. The core idea is knowing the slope or rate of change at any moment, which tells us if a value is rising, falling, or constant. Moving slightly forward in time, we approximate the new value using this slope, which indicates the direction of motion. Positive slope means increasing, negative means decreasing. The Euler method repeatedly starts at a known point, looks at the slope, takes a step, and repeats. Enough steps create a rough picture of system behavior. Imagine a curve on a graph. Zooming in on a small part of the curve makes it look like a straight line. The Euler method uses this. It replaces tiny curve segments with straight-line approximations, following many short straight segments instead of a complicated curve. Connecting these segments approximates the curve. Smaller segments yield better approximations. Large steps lead to inaccuracy, as straight-line pieces won't match the curve well, causing drift. Accuracy depends heavily on step size. Euler's method is used in engineering to simulate motion, control systems, circuits, and heat transfer. Engineers use it to understand system responses to forces and disturbances. In physics, it approximates particle, planet, fluid, and wave movement when exact solutions are too complex. Biology and medicine use it to model disease spread, drug effectiveness, and population growth, as these systems change continuously. Computer graphics and games use variations of Euler's method in physics engines for motion, collisions, and character movement. Despite advanced techniques, Euler's simplicity makes it fast and useful. Finance uses it to estimate evolving prices, interest rates, and investments when perfect prediction is impossible. Its advantages are simplicity, ease of implementation with basic arithmetic, and flexibility across various systems and equations. However, it can be inaccurate with large step sizes, errors accumulate, and sudden changes are hard to track. Due to these limitations, advanced techniques like improved Euler or Runge-Kutta methods are used for high-precision applications. Still, the Euler method is a crucial starting point for learning to approximate and simulate dynamic systems. The Euler method is a step-by-step technique for approximating future behavior of systems that change over time. It uses the current rate of change to estimate what happens next, rather than solving complex equations directly. Each small step builds on the last, forming a chain of estimates that traces the system's behavior. It is simple, intuitive, and widely used in science, engineering, and computing. Even with more accurate methods, Euler's method forms the foundation for understanding numerical simulation. It teaches us that even when the full path is hidden, we can still move forward one step at a time.